Hello, welcome back everyone. Hope you had a good break. I welcome both you that are here in person and those that are tuned in virtually. And the first talk will be, as I mentioned, slightly different. Mr. Michel Brett, the Principal Specialist for Quantum Computing at AWS, will give us a talk about how customers are using Amazon Braket to explore quantum computing in the cloud. Mr. Michael Brett, please go ahead.
Well, thank you very much for that kind introduction, and it's wonderful to be here with you all, albeit virtually today. I'm joining you from Abu Dhabi, but I wish I could be there in person in Singapore with you all to share this presentation. But hopefully, you're able to connect with some of our colleagues from AWS who are there supporting the high performance compute sessions that are on right now. But today, I'm here to share with you a little about what Amazon Web Services is doing in the area of quantum computing and how that relates to our overall high performance compute effort in the cloud. So my name is Michael Brett. I'm a principal specialist for quantum computing at AWS, and I lead our business development efforts for Amazon Braket, which is our quantum compute service hosted in the cloud. So today I'll share with you a couple of stories from our customers and also a little bit more information about what we've been up to in quantum computing at AWS. And at a very high level, the activities in quantum computing at AWS fit into these 5 pillars of activity. The first is Amazon Braket itself, and I'll talk in a lot more detail about that service and how to use it. We've also got a group called the Quantum Solutions Lab, and this is our dedicated professional services team of scientists and engineers with deep expertise in quantum computing. This is the group that works directly with customers on exploring problems, doing joint R&D together, producing original research, and helping those customers explore quantum computing and take their journey through the cloud. We've also got a group called the AWS Center for Quantum Computing. That's our deep R&D science effort. So it's not customer facing, but it's a science-focused activity on exploring hardware, software, error correction, all of the improvements that are needed in quantum computing to help bring this technology to fruition in the cloud. We've also got a partner network, groups of companies all over the world that we work with who bring expertise in not only quantum computing, but in specific domains like finance or logistics or pharmaceuticals, who we can help scale solutions with. And I'll talk about a couple of those examples as part of this presentation. Then finally, a group of worldwide specialists. So I am one of those, a specialist in quantum computing. Our job is to connect with customers and help them navigate the AWS services, including quantum computing and high performance compute, so that you can have the best experience on the platform. So there's a lot of different groups that are involved in quantum computing at AWS. These are the 5 main ones. We've all got our own job to do to bring quantum computing to fruition and connect with customers. But there's a lot of opportunity here to engage no matter what your interest level is. So if you're learning for the first time, we can engage with you there. If you're a researcher in quantum computing or high performance compute or computer science, we've got some great research activities. And then for enterprises and startups, you can build on top of Braket and other AWS services to explore this space too. So let me touch on a little bit more detail on some of those activities. The first is the AWS Center for Quantum Computing. Again, this is our deep collaborative R&D research effort. It's based on campus at the California Institute of Technology, Caltech, in Pasadena in California. We collaborate very closely with a range of other institutions all over the world, but this is an innovation center to focus on the long-term tough problems that are needed to be overcome to bring quantum computing to fruition. The kind of work that's going on at this center is focused on building out a fault-tolerant quantum computer. So a new piece of hardware taking advantage of a lot of the innovations that have come through over the past decade in quantum computing hardware. If you'd like to read more about this particular architecture and the hardware efforts that we're exploring, there's some papers available online. But suffice to say that the effort here at AWS is to build on the innovations over the past decade in fault-tolerant quantum computing, invest in our own hardware that we will eventually make available to customers, and focus on building out fault-tolerant schemes that can make that hardware more effective in the cloud for hybrid algorithms. What you see on this slide is some of the first photographs from the center. So we released these as part of the lead up to our reInvent conference last year. These are some of the first photos available of the AWS quantum computing hardware that's under development. And we'll actually have a presentation up on the AWS YouTube channel from reInvent, talking in a lot more detail about that hardware effort and some of the innovations that have gone into that hardware design. So I'd encourage you to explore that if you're interested in learning more about AWS's investments into our own hardware effort. I spoke a little bit before about our Quantum Solutions Lab. This is the team of scientists and engineers that work directly with customers on problems. The kind of work that they do is collaborative R&D, so working as part of a joint research team with collaborators to do original science and to publish that work. We also do education activities for students at universities, but also in corporate capability building. So building up the expertise in teams within organizations so that they're able to do quantum computing themselves and to build out those efforts. We're also exploring solutions with customers. So taking ideas from the whiteboard and what could be potentially solved on a quantum computer, all the way through to a proof of concept and an evaluation study to look at what could the potential return on investment be as these solutions move into production, as the computers become more capable over time. So let's talk a little bit more about Bracket itself. So Bracket is a fully managed compute service in the cloud to make it easy to explore quantum computing. And exploration really is the most important word on this slide. It's an environment where you as developers and scientists who want to understand more about what this technology is and the kind of impact it can play in high performance compute. It's an environment to design out algorithms, take advantage of all the examples that we provide in this space. You can test on high performance simulators that are very low cost and scalable, running on classical compute in the cloud. And then you can run those algorithms on real quantum computing hardware. So we make available a number of different systems. I'll talk in some more detail in a second about those. But it's an environment where you can pick up quantum computing for the first time, explore at very low cost, and try out different tools and techniques that we've got a ton of example notebooks available for you to explore in that space. So a quick look at the high-level architecture diagram for Bracket. Bracket's in the very center of the diagram there in the orange box. It exists as part of the AWS cloud. So it's a fully integrated service within AWS, an environment where you can connect into all of the other services that we make available. So whether it's S3 for storage or CloudWatch for notifications or our high performance compute assets, you can combine Bracket with all of the other services that AWS makes available. And the thing that makes that possible is that Bracket is a fully fledged service of AWS. We released it into general availability about 18 months ago. And Bracket is unique amongst the cloud service providers in that we offer a fully integrated service that allows you to combine all of the different enterprise-ready elements of quantum compute and high-performance compute into that cloud environment. So you can build on top of those services and bring solutions to fruition faster. On the left-hand side, 3 different ways for users to access the services from Bracket. First, the managed notebooks I mentioned, we've got a ton of examples there that you can explore with. A software development kit you can download and run locally, and then a GUI environment through the console. The very center of the diagram are the managed simulators of Bracket. So these are simulators that run on classical infrastructure that allow you to test out algorithms and scale them out so that you can debug and test and assess before you deploy to the quantum computing hardware itself. Where did my hardware slide go? So we've got 4 different hardware systems available today on Bracket. We launched with 3 systems from 3 providers, quantum annealing from D-Wave, ion traps from IonQ, and superconducting qubits from Rigetti. And we launched just this week, only 48 hours ago, a new system from Oxford Quantum Circuits. This is a superconducting based approach to quantum computing out of the UK. It's the first edition of new hardware to Bracket since we launched into general availability. And it's the first time we've added a new region for AWS to Bracket since general availability as well. So we've now got a UK-based region for AWS with a UK-based computer that's been added as well. So with this environment, you're able to explore multiple different kinds of quantum computing hardware from multiple different providers and test out the same algorithm and same application across those different providers. There's some nuance to this, but it's essentially one line of code to change to target these different environments. So Bracket provides you a unified environment where you can explore multiple different hardware architectures within the one system. We're looking forward to adding other hardware to Bracket over time as well. You'll see on the slide hardware from a company called QEra. They're based out of Boston in the US. They're a Harvard University spin-off. This device will be added to Bracket within the coming months and will be the first Rydberg atom-based quantum computing device added to any service in the cloud. And it allows us to take on a unique form of algorithmic approach called analog Hamiltonian simulation, which will provide another really interesting facet to the kinds of experiments that you can run on Bracket in the cloud. So we look forward to adding other hardware in time. AWS's own hardware will be added in time as well as part of this portfolio. But we look forward to connecting with other hardware developers and helping them find a pathway to get their hardware into the cloud as well. So one of the most important elements of quantum computing is the connection with the classical compute infrastructure. And I want to spend a few seconds on this because this is a supercomputing conference and we're talking about high performance compute. And it's important to think of a quantum computer as being part of that portfolio of compute. So we've got a range of performance hardware that's available on AWS in general, so CPUs and GPUs and other performance systems. But now quantum computing is one more tool in that toolbox. And we've been working hard behind the scenes on Bracket to integrate the Bracket quantum computing process into the other high performance compute assets of AWS so that it's part of one integrated environment. So you can think of quantum computing as a special purpose co-processor that sits alongside classical CPUs to do hard computational workloads. So working through a loop of, let's say in machine learning, updating parameters, running some of those parameters on the quantum computer, returning some execution results and looping through that process. So to quickly introduce one of the concepts around this, we have a hierarchy of algorithmic work that happens on Bracket. The lowest in the hierarchy is a shot. So a single execution of a quantum computing circuit is called a shot. And so that's essentially one algorithm. So defining one algorithm or one circuit that gets executed once on a quantum computer. A task then is a series of repeated shots on the device. So looping through exactly the same algorithm many, many times over. And we do this in quantum machine learning, in chemistry analysis and optimization problems on Bracket to loop through that same circuit many times. And we've introduced recently the concept of jobs. So with hybrid jobs, it's a sequence of classical and quantum compute loops that will typically loop through tens to thousands of tasks per job. So to set up the right job environment and loop through both the classical and quantum components has been a challenging thing to do in an integrated environment. But we've recently launched a new feature that manages that for you. So just a couple of months ago, we launched a new feature called Bracket Hybrid Jobs. And this is a fully managed environment to handle the jobs construct. So both the quantum and the classical resource within one environment so that you can execute any arbitrary set of code within that environment, and AWS will handle both the quantum and classical aspects of that work. So what we've done here is essentially containerized that job. So you can write a container, you can use the container services that AWS offer, and within that container includes all of the code necessary to run both the quantum and the classical aspects. And then you deploy that container within Bracket, and you get priority access to both the classical compute and the quantum compute resources to do that work. So that means that every time you loop through that quantum classical interface, you essentially go back to the front of the queue for the quantum access. This is a scarce resource today. It's really important when we're working in a hybrid environment that you're able to make use of that resource on an on-demand basis. And so by using this hybrid jobs feature, it allows you to capture the prioritized resource of both the quantum and the classical compute operations there, and build out some really interesting applications. So we're excited to see what our high-performance compute customers do with this new feature. It adds quantum processing to that portfolio of compute in an integrated way for the first time. So let's take a look at what some of the users of Bracket look like and some of the applications that they're exploring. So Bracket users typically fall into 4 categories of use. We've got our research customers, independent software vendors that are building out solutions that sit on top of Bracket, the rest of AWS, partners that we work with to help scale what we're able to do in quantum computing, and then enterprise customers that are exploring intellectual property, developing their own capability, and preparing for the future on what quantum computing can do. So with our research customers, we've been focused on building out regional partnerships, so connecting in with the leading scientific research bodies for quantum compute or computer science or high performance computing within particular regions. And so over the past year, we've announced arrangements with teams in India, in Israel, in Italy, in Japan, and the US that help us to scale out and distribute access to quantum computing resources and to help train those researchers in those areas. I'll highlight the most important one, especially for this conference, is a partnership that we've developed with the quantum engineering program based in Singapore, and particularly out of the National University of Singapore. We're really excited about this. This enables us to connect into the regional talent base that exists within Singapore, and to work very closely together on algorithm development, testing and characterization, benchmarking, to connect into high performance compute resource as well. And so over the coming weeks, you can look to us for some activities around building out the research activity to connect Singapore-based quantum computing researchers into the resources of Bracket. So we're pleased to be a part of that. Just want to give you a couple of quick examples of what researchers are doing on top of Bracket and some of the papers that we're starting to see come through referencing Bracket as a tool to do some really interesting and high quality science on top of the platform. So the first is a cross-platform benchmark analysis that was performed by a team out of Europe, particularly led by some folks at the University of Amsterdam. And this was developing a benchmarking framework that could take advantage of the multiple different kinds of computer that sit within Bracket. So it was a structured test environment to compare how the different devices performed across different algorithms, to do telemetry and tomography on top of those algorithms, and to build out an approach to scalable benchmarking. So as these computers become more capable and we upgrade them, how can we continue to update those benchmarks? Another example is an optimization problem. This was some work out of the University of La Salle, and this was a quantum algorithm development, a novel algorithm to look at an optimization problem around distance path minimization. So for robots in a warehouse, how do you optimize within a severely constrained environment? And a lot of large-scale combinatorial, highly restricted optimization problems can be adapted to suit quantum computing. And so this research team accessed the D-Wave quantum computer, the annealing device, adapted a set of existing algorithms to suit this particular problem, and then ran some benchmarking tests to assess that work. As a final quick example, there's also some really great physics-based research that can be done. So we see a lot of operational research in machine learning and optimization, but then the physics-focused research on problems like tomography, where there's some particular behavior of quantum computers that can come through via bracket. And so we're seeing physicists at universities, and this particular group out of Chicago did some great work around quantum process tomography there. So we've got this research program. We encourage researchers to get access to bracket. With AWS, we've got a program called the Cloud Credit for Research program, where we can help facilitate access to these tools and provide you with credits that help support the resources that are needed to do this work. So if you're interested in engaging with us on this kind of research, I encourage you to reach out through these channels, and we can help you get started with the program. A couple of other quick examples just to wrap up with. Just wanted to mention some of the independent solution vendors that we're working with. So these are startups that are building their businesses on top of Bracket. One in particular is Entropica Labs, based in Singapore. I believe they're talking in one of the parallel sessions at this conference right after mine, so in about 30 minutes. They'll be there with another one of our partners, Horizon Quantum. So some really fantastic new businesses that are taking advantage of not only the access to quantum computing through Bracket, but all of the other services that AWS offer. So we've got teams from the US and Europe and Japan, two from Singapore we work with, all over the world are building out those solutions and making them available through a go-to-market pathway on top of Bracket. One in particular to highlight is a company based in California called Ware. They built out a package called Forge. Forge is an environment where they've added abstraction layers of algorithms on top of AWS. So they've built out additional code that makes it easy to look at regression analysis and clustering and classification applications. They also have environments where you can manage CPU and GPU simulations within that environment, and some additional resource for learning about quantum computing as well. So we're so happy to be able to work with customers like Ware that are adding additional value on top of Bracket through further abstraction libraries, sector-specific applications, and learning resources. Another quick example at the enterprise level is JP Morgan. So we worked with JP Morgan on the hybrid jobs tool set that I mentioned before, looking at a portfolio optimization study. So I was using a particular algorithm called QAOA, which runs on quantum compute. What JP Morgan were able to do was take advantage of that hybrid jobs app tool set, combine quantum and classical resources together into an integrated environment that was part of JP Morgan's approved enterprise IT architecture. And so that was really important for them, not just to implement a quantum computing algorithm and do some good science, but to do it as part of a governed engineering assured enterprise IT infrastructure to show that pathway to deployment in the future. And one final example is some work that we did late last year with BMW. AWS and BMW teamed up together to run an open innovation challenge. We identified 4 problems that were really well suited to quantum computing from the automotive sector. So looking at machine learning for quality assessments, sensor placing around a vehicle, materials deformation QA in production, and then also optimization problems around vehicle configuration. We opened up these 4 problems to the world. We invited companies and teams from all over to submit their ideas about how to implement them, so including some code and some benchmarking analysis. We facilitated this competition. We had about 76 applications from all over the world. We ended up selecting 4 winners from this process, and those 4 winners are now engaged under contract with BMW to implement their work and further develop it. So I'll wrap up there. The key takeaways from today, Amazon Bracket is available. We've been in general availability for about 18 months now, and it's an environment to help you start exploring quantum computing. We've made a long-term commitment to quantum computing research at AWS and partnering with the likes of the Quantum Engineering Program in Singapore to explore this science and to help bring it to the world. And we've got customers and partners that are building out applications and expanding that capability, particularly as we look to the quantum classical hybrid nature of this work and bringing out high performance compute workloads into that environment as well. So we're excited to explore with you and to build out this capability even further. Thanks for your time today.
So thank you, Mr. Michael Brett, for this insightful talk. As you can see, there is this prevailing theme in this track. Various vendors are talking about the convergence of HPC and AI. And then we have another stream where you have vendors talking about quantum computers and quantum technologies. Our next talk is by Dr. Bill Nitzberg, CTO at PBS Works Altair. And the title of his talk is Delivering Breakthrough Results for All in the New Multidimensional HPC World. Dr. Nitzberg, thank you.
Hello, I'm Bill Nitzberg. I lead the HPC and cloud teams at Altair Engineering, and I'm going to talk to you about delivering breakthrough results in the new world, which is really a multidimensional HPC world. First, let me just tell you what's going on at Altair. Why Altair for HPC? Let me remind you, probably many of you have seen us over the years for a lot of time, but there's some really exciting things that happened in the last couple of years, and I want to tell you about them, and I want to tell you why I think they're really taking us from a world of doing incremental improvements to truly breakthrough results. So Altair absolutely knows HPC. So we have amassed the greatest number of people and with the biggest depth of experience in high performance computing in workload management and job scheduling with our recent acquisitions of Runtime in the EDA space, with Univo, with Grid Engine and NavOps, and with Alexis in IO management. Really nobody beats Altair in high performance computing. Thousands of customers, millions of cores managed every day, billions of core hours delivered, and really trillions of core hours delivered overall. I mean, when I think about HPC, I think Altair really knows HPC. Okay, what is HPC today? Well, I've been around for a long time, and many of you may have seen me before. When I got my start in HPC was really about big iron. There was one big, I don't know, maybe even back to the, I don't want to say how old I am, back to the Cray days, there'd be one big computer, basically one big node. Maybe it had multiple processors, memory. You know, in the Cray days, the most important thing, even though there were, say, 8 processors in some of the original Crays, the most important thing was how do you allocate memory to best deliver the most that you could out of this multi-million-dollar machine. And then through the years, through the decades, really, not too much has changed inside of what we're doing with HPC scheduling. HPC has really been about the compute node. You know, we've put other stuff in it. There's CPUs, there's memory. You know, today there's really high performance GPUs. There's NVMe devices for storage and stuff, but it's really still inside this one package. And in some sense, you know, you bought it. There was some resources that you owned, and you just needed to make the best use of those resources you could. And in that sense, one node, HPC has really been one-dimensional. It's been exciting, especially for folks like me, because there have been all sorts of changes inside of that node, like I said, with GPUs and CPUs and everything. But really, it's been what I'm going to call relatively easy to do the scheduling because the scheduling has been one-dimensional. But in the last few years, maybe the last 5, maybe up to 10, really the last 5 years, there's been actually an explosion in the dimensionality of high performance computing. It's no longer that we own our resources and that there's just really CPUs, memory, maybe some accelerators to deal with, maybe a network connecting them together, still pretty one-dimensional. So what's happened? Well, the first thing that's happened is software. So software has become no longer something that every little HPC organization builds on their own, but huge industries are selling really fantastic high performance software. And in some industries, like the EDA semiconductor industry, software is actually the major expense that you're spending in high performance computing. There can be software that is at $1 million per seat. So compare $1 million a seat with something that you're buying. Maybe you're buying a really big computing system. Maybe it's $10 million. Well, that's only 10 copies of the software. Getting the most out of your HPC system now in a market where software is expensive requires that you not only schedule HPC infrastructure, CPUs, GPUs, memory, even across networks, but you actually take software use into account. So that software is adding this extra level of dimension, this new piece of what you have to actually schedule. It's making it, for me, more interesting, so I like it. But software is actually, in some sense, looking a lot like compute in that you buy it, you pay for it, and now we just have to schedule it and manage it, and we have to get you the most we can out of it. What else is happening? Well, an explosion of data that requires us to actually think about storage, to think about where your data lives, to think about how you access your data. I mean, especially with the addition of data analytics, AI, ML, huge quantities of data are now being pumped into the system, even more so. I mean, HPC has always a lot been about data, and especially in markets like weather and stuff, there's been huge quantities of data, bioinformatics, but even more so today with AI. And it's way more important now that not only do we look at compute nodes and software, but we actually manage all of that data, the data locality, access to the data, when we're accessing the data, where we're accessing the data, and we make sure that we don't overstress the storage system, thereby slowing everything down. And so scheduling for storage, scheduling for I/O has become yet another dimension that we need to add to the HPC space. Third, we're adding cloud. Cloud is actually an interesting dimension because it's not a dimension where we're adding something new that we didn't have already in terms of compute nodes or in terms of the software license or in terms of the storage that we have to deal with. It's adding another level of a truly new dimension in a different direction. It's adding, going from on-prem, we own everything, to an on-demand, we're going to buy it as we go kind of system. And this extra dimension takes us out of the how do I truly optimize use of things that I already own to when do I optimize things that I really own and when should I go buy something that I don't own in small pieces. It also opens up a huge new possibility, which is maybe I don't need to own everything. I can own some things and purchase and rent some other things. And so cloud is this truly other dimension that's taking us in a different direction, but a direction that's super important in terms of how we have to manage our systems now in high performance computing. So high performance computing has gone from sort of what I'll say again is one dimensional, we just had compute nodes, sophisticated compute nodes, or even clusters of compute nodes, to compute nodes, software, storage, and a new way of accessing these, and we have to actually meld them all together. Well, to get that to work, what we need to add is 2 more things to the mix. We need to add some way now that we didn't care as much before about, but of cost management, of cost controls, of budgeting, because although the cloud is infinite, nobody's budget is infinite, and you don't want to spend an infinite amount of money just to get your HPC done. The old days of, hey, we got approval for going and spending $5 million or even $500,000, whatever the budget was, and now we just need to use some scheduling software to get the most out of that, is now, hey, we could spend, well, an infinite amount by going to Azure or Amazon or Oracle or Google. And really, although I'm sure the cloud providers would love you to spend an infinite amount of money, not too many people actually possess that. And so cost controls, budgeting, is actually a key component now of how you actually have to manage this new world. And finally, the new world is no longer something that you can do in part because of cloud, but in part because of just the speeds and the velocity of everything that's going on. You really need automation. And so to this multidimensional world, you need to add automation. And that's what I wanted to say about where we've gone from single dimensional, what I'll call single dimensional HPC of yesterday, into a truly multidimensional world with CPUs, licenses, storage, cloud, and then that actually brings us to requiring some kind of cost control, some kind of budget management, and tools for real modern, code, infrastructure as code, DevOps kind of stuff in the HPC world. Now, Altair has gone from actually having a fantastic solution in just the one-dimensional HPC world space to acquiring, as I mentioned, fantastic companies that cover the gamut of the rest of this multidimensional HPC space, with the runtime software now called Accelerator and the Accelerator product suite doing fantastic software license scheduling in addition to job scheduling, with the Alexa system doing fantastic work in I/O profiling, helping us do storage-aware scheduling, and in cloud, with adding of the Univa NavOps system, we can take some of our home-built cloud stuff and we can really take that cloud technology to truly roll it out with full automation engine that came with NavOps and cost controls. Okay, so now what does this give us though? We've gone from something that we had some one-dimensional stuff where we really could truly optimize the return on investment you were getting. And that's really important. Return on investment is fantastic. And actually we can see that in HPC, we've been able to get you 20, 30, 50, sometimes even 1 times return on investment, 100% return on investment to optimize what you're doing with your cloud. But optimizing what you're doing is really a bottom line focus. You spend some money or you're about to spend some money, you want to get the best return on that money. What I've seen HPC happen and what we can deliver with HPC now by bringing all of these tools together from all of these different places is we're going from a world, an old world of one-dimensional HPC to this new world of multidimensional HPC, to a world in which we're taking bottom line return on investment and we're truly making it a top line revenue generator. But for a top line revenue generator, which is going to generate really breakthrough results, let you leap ahead of your competition, let you get more research done that you couldn't possibly do before, let you do things you can't do before. You can't have 10 or 20 or 50% better. You really need to do 10 times better. And that's what we're seeing now in HPC. That's what we're delivering at Altair. That's where our focus is in Altair on HPC, is delivering not just return on investment, but truly delivering breakthrough results. And I just have 3 examples that I'll give you here. So one is 10 times better turnaround. We have a fantastic partnership with Ping Golf. Ping Golf is now saving almost a half a day every day processing what they're doing. So going from doing something once or twice a day to doing something multiple times a day it's really a breakthrough change in how you can design products for them, golf clubs. For you, maybe it's whatever product you're designing or whatever science you're delivering. If you can deliver 10 times more, you're not going from, hey, we're a little bit better than we were, to now we're delivering something that, boy, we couldn't even dream of delivering and getting out the door. We've delivered now 10 times better throughput. At Infi, now owned by Marvell, our accelerator technology is delivering 10 times more throughput than anything else that they've seen. 10 times is breakthrough results. And finally, just in scale, we're now working with Argonne National Lab in the United States, one of the Department of Energy labs, to build one of the first exascale computers, 10 times bigger than anything else that exists today, using the PBS Pro technology. I've taken you through sort of a little bit of a history from where we were decades ago in high performance computing, where we were doing a great job of optimizing sort of a one-dimensional HPC world, to today where we have a truly multidimensional HPC world that requires way more sophistication, cost controls, automation in order to make. But what you get for optimizing this multidimensional world is you truly get breakthrough results. And today, in Altair solution space, we're actually bringing all this together. We're bringing together complex scheduling, high throughput scheduling, storage-aware scheduling, the ability to migrate and automate moving to the cloud, I/O monitoring, I/O profiling, portals for remote visualization and job submission, just HPC management, dependency analysis, license scheduling, license monitoring, containerization, cloud bursting, and again, cost controls in a world that we can apply both on-premise and in the cloud. Today, we have a more expansive solution set than I think anybody does in the industry. And really, I truly believe that Altair knows HPC. Anyway, I hope you've enjoyed my little bit of a history lesson and taking you through where we started in high performance computing and scheduling and workload management and where we are today and why I think it's so important it's just a breakthrough change really to deliver breakthrough results today that we can do that we couldn't do before. But by bringing all these technologies together, we can actually truly, truly deliver breakthrough results. Thank you.
So thank you, Dr. Nitzberg. And there is just a small change in the next speaker. The title of the talk is is How Atos is Boosting Scientific Research and Large-Scale Simulations Thanks to the Combination of Machine Learning and HPC Expertise. The talk will be given by Dr. Xavier Vigouroux. If you may remember him from the previous session.
Exciting one. Okay, the sound is okay? I can remove it? Okay, thank you. Yes, definitely. Yes, I was here a few hours ago for a presentation about life science and the Center of Excellence that we are launching there in Cambridge. So this time I will speak about AI in the context of the HPC and how AI can be beneficial for the HPC for numerical simulation. So I'm not Cédric Bourrasset. Cédric Bourrasset is the one who should have presented this session. I'm Xavier Vigouroux. I'm a background in HPC. I will try to do my best to take over from Cédric. You know that for the COVID reason, he was unable to join. Hello, Cédric, if you are here. I know you can listen to me. So let's go to the first slide. So this morning also I presented the vision of Atos. So Atos is a HPC provider for 15 years now. So there are three pillars in our domain. The first one is HPC, so pure hardware, integrating the best technology with CPU, GPU, IPU, QPU, all the PU, plus different networks, different storage. The goal is to be at the top level on the top 500 list, and also to address I would say, smaller configuration. So HPC, we know how to design hardware, and we know how to make them work with application. The second pillar is AI. So AI is solving issues that we are unable to solve by other context, or that may be more efficient to solve these issues. So again, as this morning, I named Yann Lequin, who said that there is no way to write a program. He doesn't know how to write a program that would recognize a cat in an image. And definitely AI can do that. So clearly, some problems can be solved by AI, and that cannot be done by HPC. The third pillar is quantum. So quantum is more a promise. It's something that we know that will be a game changer in the near future. So, but now we don't have the QPU ready yet for the production level at the right TRL level. But nevertheless, we know it will come. So with them, they are today noisy, they have some limitation, but it will be a game changer. So we are already working on that in Atos to train people and to make people ready for this revolution that will arrive in a couple of years, let's say to 2025, 2026. They will have to be ready to change their application and to understand how quantum is working, and also anticipate the quality of the result they will obtain thanks to compute computer. And QLM, quantum learning machine, is here for that. So we have these three pillars, and HPC and AI, in fact, get benefit from each other. HPC and the hardware coming from HPC makes it possible to train very large models, huge models, as we can see today. And also HPC can be used for synthetic data. Synthetic data can be generated by the HPC and be used to train AI model. And the other way around, AI can be used to replace some numerical part of the HPC and of HPC workflow because it's more efficient. This is what I will cover here. In terms of hardware, again, this is the presentation that has been made by Agnès Boudot, the head of HPC in Atos, this Monday, considering our new offer, the XH3000. So it is designed to make any scale, I would say, from one rack, so let's say a petaflop, to an exaflop, so many, many racks. It's very versatile in terms of what can be put in terms of CPU and computing power, CPU, GPU, QPU, this is what I said. And there is one very, very important aspect is the cooling system. This is direct liquid cooling system. So we are able to cool it down with 40 degrees water. So here, with water that you have here, you can cool it down. You don't need to have chilled water. You don't have to have chillers. You just have a pump to cool it down. So in terms of efficiency, the cooling doesn't cost 30% of the energy as it was the case before. So this is for the supercomputer as an introduction. So let's move now to the focus that, of this talk. This is the convergence between the HPC and the AI. And as I mentioned, we are developing supercomputer with hardware that make it possible to train models, ultra-large models, but also we enable some numerical workflows with AI parts. And here we have done that in different contexts. And the first one is that we have understood that there was a limitation in terms of scalability. Numerical kernels may not scale up to the level that we want. And so we can just replace it by a data-driven approach. The issue is that when you are doing that, you are changing the paradigm. The scalability that you were used to have with some kernels, because you have a loop nest or something like this, that you know how it will scale, you know how the data will scale, suddenly you will change that to have some data-driven plugin or component that you will have to manage. So the orchestration has to be changed. The way you manage data will have to be changed. The assertion, the way you develop the DevOps will change to something with some ML, machine learned approach. Everything is to be changed. So what is sure is that today we have to couple the both models as a new way to improve the performance of the simulation, for instance, for weather and climate models. So if we look at all the components that we need, in fact, to reach and to active these levels, in fact, we need several aspects. The first thing is to design specific models that will be used for specific usage. Obviously, what you will do in CFD will not be the same as the one you would use in weather forecast, and every model has to be trained, to be designed also in terms of architecture to achieve a specific goals. So first of all, we are designing our own models, and we are putting some of them in an open source system. The second aspect is that we have some teams that can be used for a specific tailorization of a model. Consider, for instance, CFD. You can say, okay, I have designed a model with the right architecture. I know how to train it. I have a general model for CFD, but in a specific context, you may need something more fine-tuned, and then you can use our team to fine-tune this model. Once we have done that, obviously you need efficiency, and if you need efficiency, you need orchestration to be sure the data in, data out, and the way you will schedule your model, to be sure you get the efficiency you have expected. And finally, and I think this is very important, is that thanks to the HPC, you can do some kind, I would say, active learning. So the fact that you will improve the quality of your model and the quality of the result you will get from your model, because you can you can select the data you want to feed, with which you will train your model. If you consider, for instance, in a given domain, the quality of your model is not the right one, then okay, let's go back and let's do a retroactive loop where you will get data refinement exactly where you need to have it. And thanks to HPC, you can do this loop quite efficiently. If I do the same thing, if I write the same thing with more in details, we have exactly the 4 steps I mentioned with AI4Sim. So open source model collection, something you can get. If you want, you have the workflow orchestration in terms of how to integrate that in the conventional solvers, as is mentioned here, and to be sure that it's efficient in what you want to achieve. Active learnings, this is what I mentioned as the last point, and obviously tailored, given some tailored models if you need to. So if we move again further, we did that for the weather forecast, okay? We already proven this performance improvement, and I will show you in the next slide. We already proved that for a strong player in weather forecast in Europe, that we have been able to improve the quality of the result. But we are working also in ocean and climate modeling, and also in CFD, as I mentioned. The 3 rows that we can see underneath is in fact the fact that we are relying on people. Okay, we have different level of peoples and patents and experts. We have the ability to rely on different hardware. Again, Atos is an integrator, very flexible in terms of component. And so we are integrating CPU, IPU, for instance, the GRAPHCORE ones, NVIDIA GPU, all these things. So we are very versatile in terms of hardware. And finally, we have partnerships. So you have some names known in France or in Europe, INRIA, CEA, Cerfax, NET, and some projects as RAISE. There is one logo, the logo of ECMWF. So ECMWF is a weather forecast, medium range weather forecast company, institution, I would say, in Europe, currently based in Reading, close to London. And we have a center of excellence shared with ECMWF. So we have ECMWF on one side, and they are Atos on our side. So we are providing them the computing power, so the machine on which they will run this the weather forecast, really the production. And beside this supercomputer, we have a center of excellence to collaborate on the new, the emerging technologies. So there are at least 2. The first one is GPGPU, how they can rely efficiently on GPGPU, because today it's not still 100% use. And the second thing is how we can rely on AI for changing some parts of the workflow, exactly as I mentioned, changing some part of the workflows with AI components. So we had different topics. There are many. Yes, we have different actions, emulation of physical parameterization schemes. The first one, always the goal is to have something quite generic, so vanilla solutions, as they mentioned. Some, yes, you can read with the feature detection, all that thing. And we have already worked on a specific aspect of this workflow to forecast the weather, and this is what is called the orographic and non-orographic gravity waves. So this is a good example. This is very computing intensive in the workflow, because it's a very fine grain, and the grid needs to be very refined, so it costs a lot of energy. And this is, if you look at the mountains on the right, you can see the orographic drag is the fact that when there is some wind, you have some waves behind the mountain, and you have to simulate that correctly. So this phenomenon is to be simulated and to be integrated in the weather forecast. The issue is that it costs a lot. So we took 4 versions. We took the traditional simulation version, and we took the one with neural network. So if you take the CPU base, you can see that there is no real benefit from the traditional version compared to the neural networks one. 300 seconds in both cases, you can say it's not there's no key advantage. You can say there is some higher precision. We have to consider what is higher precision in this context, but let's consider this is on par. Okay, CPU is on par. But we know that when we are going on GPU, as we are relying on a framework very optimized with a neural network on a GPU, then we get a huge benefit. So this is, in this case, 4 seconds instead of 300 seconds. The key point is that we don't have the duration of the traditional simulation on the GPU. And this is a key aspect. The fact that if you want to port this numerical algorithm on a GPU, you have to write everything from scratch and to reorganize all your code to have it ported on GPU. It's a very tedious problem, I would say. Here, the fact that we are constructing the solution with neural network, you have the key advantage of all the environment and you have all the libraries that makes it working on GPU quite straightforward. So here we got no result for the GPU-based version in traditional simulation, whereas we have the AI solution. The question is, what would be the performance of the traditional simulation on GPU? Maybe it's better, maybe it's worse. What is sure is that it will cost if we want to do that. So today, we are able to do that. So this slide, for me, is important in what we can achieve and what we cannot achieve. A second example is with Surfax. This is Combustion. So here we are taking, yes, we are considering a company doing combustion in a turbine as the one you can see on the right. And the goal is to do CFD. So from step 1, step 2, step 3 to see the conditions of the domain with the combustion, just you can see on the bottom right. And we can see that there are performance improvement at this stage. The result is to be validated again, because we have to be sure that the results are in line with the expectation. So today, this is only one part of the full simulation that is done here. Okay. Regarding the open source domain list, so as I mentioned, the models are available as open source. So you just get the GitHub here. So you can get all these models. They are not tailored, I would say. If you want to tailor, we have the people to tailor this model. You can go there, be part of the community, and see what you can do with that. So the question now, we know that we can change some part of the work simulation to AI. We know that we have HPC. The question is, however, how we know how things will scale. If we do a small test on a small number of nodes, we can say, okay, we know how to write codes, we know how to write numerical kernels and loop nests and being sure that the communication is efficient. We know how to write legacy codes. The question is how things will change when you will have a lot of AI, when you will have a lot of different models in a machine, how you orchestrate all that thing, how you deploy all that thing, how you validate all that things, how it scales. There is a lot of questions still to be solved. So we are really at the beginning of this era where the AI will change some parts, probably not all the parts of a simulation, but the useful part will be taken from that, and the MLOps, or I would say the management of this model will be efficiently orchestrated, data will be understood, everything will be done. So there is still a lot of steps to go forward. We are contributing to doing these steps at this stage. Let's see the future for that. I will skip this one, just more on the open source, and this will be the end of my presentation. Here. Recorded, by the way. Okay? Okay.
Thank you, Dr. Vigouroux. It's good to see how a problem, as it was mentioned, that would entail changing the code brutally, okay, pardon my exaggeration, from like a CPU to a GPU optimized one, can be greatly simplified by using AI. This is really a great achievement. Moving on, our next speaker is Professor Yu Yang from NUS, National University of Singapore. The title of his talk is Colossal AI, a unified deep learning system for large-scale parallel training. Professor Yang, the floor is yours.
Okay, good. Yeah, thank you. Thanks for introduction. Yeah. So today the topic of my talk is colossal AI. It's a new distributed AI system. We actually opened the source code on GitHub. If you are interested, please check our code. Yeah. So here is the outline of my talk. So firstly, I will give you some background information, and then I introduce the key techniques, and then I give you an overall picture of our colossal AI system. Okay, without further ado, let's go to my talk. Okay, yeah. So as I mentioned, so the first part is the background. So here, let me show you a figure. The horizontal axis is time or timeline. For example, year 2013, year 2015, year 2017. So the vertical axis is a computational cost for AI models. And here we know is AlexNet, which kind of is first impressive AI models in the last 10 years. It's the first one. It's a starting point for the new AI solution. Yeah. So here AlphaGo or AlphaZero is a very famous, very popular AI models. We know that. Yeah. From this figure, we can see. So the computational cost of AI model actually they can increase 35 times for every 18 months. However, even we have Moore's law, we know the computational power of our chip, they only increase roughly 2 times for every 18 months. There is a huge gap between the demand and the supply. So even we have some specialized hardware like TPU, it's still not enough. So let me give you another figure. Again, the horizontal axis is a timeline. Year 2017, year 2019, year 2021. And the vertical axis is number of parameters in the AI model, or the size of the AI model. Higher means that the model is larger. From here, we can see if we count from 2016 to 2021, so the memory cost or the size of AI model increased roughly 40 times for every 18 months. However, if we count from 2019, the size or the memory cost of AI models increased 340 times for every 18 months. It's really crazy. We know the memory capability of our hardware is the speed even slower than the computing cost growth, right? So computational growth, as I mentioned, 2 times. But for the hardware memory growth, probably it's only 1.5 or something like that. So from the data here, we can see there is a huge gap between demand and the supply, and this gap is going to grow. Unfortunately, that's the bottleneck of the future AI. I think probably one of the most important thing for future AI. How can we scale up the AI on the supercomputers or cloud? So probably there is only one possible solution. I mean, without quantum computing, I think we the next 10 years or 15 years probably quantum computing is still not good enough for us to do supercomputing. So we needed to use the traditional computers to solve this problem. The only solution is to do parallel and distributed learning. Okay, that's why we designed a new model of classical AI. So our idea is we hope we use this model to automatically and dynamically help the user to develop their laptop code or their desktop code to cloud and supercomputers. Because in the future, the AI models, as I mentioned, are becoming larger, and the computation are becoming more complicated, and also we have more complicated hardware, and our hardware is primarily for the AI chips. They are very diverse. We wanted to minimize the deployment costs for the AI users. We just wanted the AI users, they spend like 2 hours to finish the implementation and then automatically develop their AI models to cloud and supercomputers. Otherwise, if the cloud and the distributed computing is very complex, without this, they probably need 3 months or 4 months or half a year to deploy their AI models or code. That's very bad. So that's why we want to design a new system, classical AI. Okay, let me also briefly review the existing techniques. So how can we make full use of the supercomputers for large AI models? There are some interesting solutions already from industry, like Maxtron from NVIDIA, DeepSpeed from Microsoft, or TensorFlow, GPipe, Gchar from Google, and FairScale from Facebook. So the key idea is 3D parallelism, data parallelism, mode parallelism, and pipeline parallelism. They are efficient, but I think not efficient enough. Let me briefly introduce the overview of our system, and then I will give you more technical details. So for us, eventually we want to build an abstract layer. With this abstract layer, so the AI users, they just need to write the code on their laptop or the desktop based on the AI framework like TensorFlow, PyTorch. And we want to make this as simple as possible. And for the complicated performance-related issues like optimization, distributed training, parallel computing, or efficient memory system, we will build them in a black box. And the users just need to give their single node or laptop code to us, and then we can automatically help them to deploy their code, the AI code to supercomputer or cloud. So we want to maximize the computational efficiency, minimize the system runtime, minimize the communication, and the most important thing is to minimize the deployment cost. Yeah. So now let me introduce the key techniques of our system. So we want to make full use of, automatically make full use of the supercomputers or thousands of GPUs, CPUs on the cloud. So the most important thing is how can we generate or how can we find enough parallelism for deep learning. So for deep learning or the neural networks, so where the parallelism come from? So parallelism can come from three main directions: data parallelism, pipeline parallelism, and the tensor parallelism. So here, for data parallelism, the idea is simple. We just partition the data to different servers, and then we do an all-reduced operation to get the average of the gradients. And pipeline parallelism, we do a micro mini batch, which makes different. We essentially we are building different pipes. Those different pipes, they are on different stages, and they use different they computing different data points. Okay, and also tensor parallelism, we partition the model within each layer and partition the different parts of layer to different servers. And so here, as I mentioned, the existing solution like Megatron and DeepSpeed, they are for Megatron, they are based on tensor parallelism and pipeline parallelism, and for DeepSpeed, Microsoft DeepSpeed solution, they are essentially more about the data parallelism, and then also they have some sharding techniques to reduce the memory costs. So for us, we want to build a comprehensive system. We want to integrate all the parallelism techniques and then automatically deploy the user code. I mean, automatically transfer a single node code or laptop code to a supercomputer code. Yeah, so here the idea is firstly we need to get enough parallelism. So for us, and we have pipeline parallelism, we have data parallelism, and also we introduce or propose some new parallelism like sequence parallelism, and also we also optimize the tensor parallelism. So for NVIDIA Megatron solutions, they only have 1D, and we introduce 2D, 3D, and 2.5D. Okay, yes. So so here, let me briefly introduce the key idea. So for tensor parallelism, for example, 2D, which means we partitions because eventually it's matrix multiplication. We transfers AI computation, the training computation to matrix multiplication. We partition them to 2D, and the 2D means different nodes. They just need to communicate with the nodes in the same row or same column. And for example, we have Q square nodes. They only need to communicate with Q nodes. For example, Q is 100. Q square, which means we have 10,000 nodes. And if they have 1D solution, they need to communicate with 9,999 nodes. But here, 2D solution, we only need to communicate with 99 nodes. And for the first 3D solution, and we essentially partition the computation into three directions. For example, if we have 1,000 nodes, it's 10 by 10 by 10. So for the 1D method, they each node needs to communicate with 9,099 nodes. So for here, it's 3D solution. Each node only need to communicate with 9 nodes. So the computational cost, the communication cost will be much lower. That's our brief solutions, 2D approach and 3D approach, and also actually we have 2.5D tensor parallelism. It's kind of a combination of 2D and 3D. Yeah, it's more useful for some specific case. Yeah. And here, let me show you the results. So clearly, and the 2D and the 2.5D approaches, they are better from the Megatron, which is 1D. So here, the horizontal axis in number of GPUs, the vertical axis is time. Lower is better. Lower is better. So, for example, here we have 64 GPUs. Clearly, 2D is much better than 1D, and 2.5D is better than 2D. Yeah. So here, here also horizontal axis is number of GPUs. And for some reason, so here 2D is worse, but 2.5D is better for here. And also, so here is a 3D solution. Okay. So here the horizontal axis is number of GPU, vertical axis it also shows the time. So clearly you can see 3D is better than 2D, 2D better than 1D. Okay, I finished the introduction of our 2D 2.5D 3D parallelism. So how about we introduce a new parallelism, a sequence parallelism? So for here, the idea is the memory cost of the data of the future data probably also very high. In the future, we probably have very long sequence data. So if we want to process and very long sequence data, and one data point, for example, can be 100 GB or 500 GB, we need also to reduce the memory cost of the long sequence data. That's why we propose a new solution, sequence parallelism. Let me briefly show you the idea. So, which means we partition the sequence. For example, a sentence is a sequence. A sentence has different tokens. Let's just partition this sentence, and later we after partition we just use the different devices to process them. So we know now the most popular AI model is transformer. So for the MLP layers, probably doesn't matter after we do the partition. However, for transformer layers, they have a data dependent. So when we compute the self-attention or the attention score, this device may need the data on all the other different devices. So, which means eventually, if we want to compute all the self-attention, if we want to compute all the attention scores, we needed to make them have an O2O communication. That's very bad because the communication overhead of O2O is very high. So to avoid that, we propose the ring self-attention, which means for each step we send firstly we compute our attention score, and then we just send our key to our right hand side neighbor, and also get a new key from our left hand side neighbor. So in this way, we just need to do P-1 communication messages. So P is the number of devices. So the auto, we know the communication, the number of the communication cost is P squared. So here we reduce communication cost from P squared to P minus. And after we finish a good implementation, the signal parallelism is very efficient. So here is a comparison. For example, if we only use tensor parallelism and only use signal parallelism, clearly we can see our approach is much better, which means we have the much low memory cost for here. The tensor parallelism takes the auto memory. And also, so here horizontal access number of GPU vertical access is so here base size. For our 6 parallelism approaches, they can use larger base size, and also we have much higher speed. And I just finished introducing the sequence parallelism, which is a new parallelism, and also the tensor parallelism. And now let me also introduce how can we make, how can we maximize the data parallelism. So here the concern for data parallelism is we increase the base size to very large. However, after we maximize the base size, we lose accuracy. So here the horizontal access is epochs, vertical access accuracy. Clearly you can see if we maximize the data parallelism like by training, they lose accuracy. And the problem was studied by Intel. The idea of Intel is it's a Shah-Mima problem. So we want to avoid the Shah-Mima problem. So we need to propose some new solution. For example, we propose the Larson-Lam optimizer. For Larson-Lam, the key idea is we use layer-wise adaptive rate scaling. We make different layers, they learn at different speed. This way, all the layers can learn very well and quickly, and eventually we can solve this problem. So here is the results after we use the Lars, for example, Lam. So here horizontal access in number of epochs, vertical access accuracy. Clearly, you can see even we increase the base size to 32K, we can get the same accuracy in the same epoch. So which means we increase the base size by 8 times, we reduce the number of iterations by 8 times. We need a much fewer number of iterations. Here horizontal access is number of iterations, vertical access is accuracy. So and that's how we reduce the VIT Vein transformer training time from 73 hours to roughly half an hour. Okay, so I think I'm running out of time. So let me just briefly finish my presentation. And in the same thing, in the same way, we will reduce the burn training time from 3 days to 76 minutes. And our solution, according to peer-reviewed code, this technical website, our approach are widely used many different AI applications. And also in the last 3 years, people reduced the image training time from 3 days to image training time from 29 hours to 29 seconds. So actually, since 2017, all of them use the our large algorithm by Berkeley, Tencent, Sony, Google, Fujitsu, and Google again. And we also got the best paper award of ICPP. And Turing Award winner Jeff Hinton, they use large for self-aware learning. Large is being used by Google Sinclair, Facebook Seer, and DeepMind BYOL system. And also it's widely LAM also widely used in many applications. And according to NVIDIA public GitHub, so here is a screenshot of NVIDIA public GitHub. So LAM is 72 times faster than previous approach, which can maximize training efficiency. And also we have an efficient memory system, which means we implement the Zero technique by Microsoft. Yeah, I have 1 minute left. Let me just briefly sum up our system, Classroom AI. Eventually, we want to build an abstract layer. So the user, they just need to write the code on laptop, and we automatically help the user to deploy their code to supercomputers or cloud. And there are many features of our system to make it easier for user to design and implement. Yeah, so it's very easy to use our system. For example, Python user, they just need to change a few lines of code. Yeah, I'm going to skip the results because I'm running out of time. Yeah, so our results are very good and we are better than the previous approach like Metron. Okay. Yeah, so if you have any questions, please feel free to ask. And also, so here is our we opened the source code on GitHub. If you like, you can check. We also have a tutorial. Okay, thank you so much. Please let me know if you have any questions.
Thank you, Professor Yang. Very interesting talk, and really congratulations on your work that you've done with Colossal AI. And this brings us to the last talk for today. It's by Mr. Rob Mollard, APAC Senior Data and Storage Technologist at HPE. And the title is Data, the New Frontier for HPC and AI. Mr. Mollard, the floor is yours.
Thank you for that. So let's proceed. Basically, we're living in a world today where everything is interconnected. We're carrying devices on our body and watches and wearables and phones, and everything is transmitting data, it's collecting data. We're looking at augmentation within manufacturing and other industries to actually assist and simplify the process for error detection and building out new models very quickly within those environments. We've got traffic and traffic controls and cars and trucks, buses and trains and all types of transportation with sensors all over these vehicles, gathering data and sending that into central data centers where that information is processed. We've got real-time computing that's happening at the edge through purchasing organizations. Wherever you go, you're using, tap here, tap there. All of these transactions and all of these things that are happening are doing real-time processing at the edge. They're sending huge amounts of data in small little segments into central locations where they can then be cross-referenced and collated and assessed against other data sets to derive insights from. And this in itself means that there are signals everywhere. From a movie, one of my favorite movies called Serenity, Mr. Universe said, "You can't stop the signal, Mel." And this is never more true than today. Today, we're living in a world with all of these things that are sending signals everywhere, and all of this data is going around the planet all the time. We've got radio signals, we've got microwaves, we've got satellites that are beaming data down to the planet, as well as sending data from the planet up to these satellites. So data's going everywhere all the time, and you can't stop the signal. So with all this data that is going around everywhere, we've got lots of different companies that are looking at mining it, and they're mining it to create insights into what's going on in those types of areas. And it's huge amounts of data. I mean, Walmart alone is using big data analytics to analyze every aspect of people's movements around their online presence. What are they looking at? How long are they spending looking at these different objects? And that's to take that information and use it for personalized advertising and targeted advertising and encouraging people to actually procure more than what they may have wanted initially. Their database is gathering 40 petabytes of data per day. Now, they can't keep all of that data, but this is doing real-time analytics on what's happening on a daily basis, and they're processing that. So it's transactional data. There's also all the data from human interaction, where I spoke about, the wearables that we're wearing that's gathering information, our phones and stuff, but people themselves are using these devices as an extension of our bodies, as our eyes and our ears, to capture our experiences, and then we're posting them online on social media activity, and this is generating huge amounts of data. I mean, Facebook alone is doing 4 petabytes of data a day with 2.2 billion active users. So significant amounts of information that are being gathered. And this is just from us creating it, individuals out in space, out in the streets and looking at things and doing stuff and actually posting our experiences. We've got digitization of analog reality that is out there, and that in itself is basically digital cars with digital interfaces for gathering telemetry data. They've got LiDAR, they've got cameras, and they're grabbing all of this analog content and then converting it into a digital presence as they're capturing it, and then analyzing that against a lot of other different vehicles on the road. Currently, we've got about 1.4 billion cars on the road today. Not all of those are enabled with all sensors, but just about all of them have some sensors of some description that are gathering data. And that data is either transmitted automatically back to some central location in some of those vehicles, and in other cases, that data is downloaded when the vehicle is taken in for maintenance. So if we think about the car analogy, cars these days, especially new cars and electronic cars that are moving towards full autonomy, are getting more and more sensors. We've got front and rear cameras, we've got LiDAR detection systems, ultrasound sensors, we've got radars, and they're all trying to create this full spectrum view that is completely surrounding the vehicle to be able to identify any type of dangers or warnings that the driver may need to be aware of. And this is part of the progression towards full autonomy, where we want to be able to have those cars to be able to drive themselves all the time under all conditions and under all circumstances. That alone, with a huge number of sensors on a single vehicle, is going to take a significant amount of computational power, so computing at the edge, moving through network pipes, whether that be satellite based transmission or some sort of wireless transmission. But what we know is that's going to have to be around 25 to 40 gigabytes per second to enable the amount of data that's getting captured per vehicle to actually be able to push that to the edge. Now, in some ways, we've kind of been lucky with the pandemic and the global supply chain and the silicon manufacturing issues that we've run into, because it's actually slowed this down somewhat. A lot of cars are getting manufactured with less sensors now because of the lack of silicon and the global supply chain issues that we face. But we are still staring down at this huge amount of data that is coming in the pipeline as new vehicles come online, and we use more and more of those sensors to be able to gather the data to gather insights and actually make decisions about that. And the reality is, this data, when it's turned into knowledge, it is power. These companies out there that are gathering all of this information, it enables them to be a lot faster in making decisions. For example, if it's an online store, they can make forward projections based on how they're selling products. They can make decisions based on individual marketing to people to encourage more purchasing of their products. They can use it to provide insights into costs associated with the transportation of their goods, times it takes to move these goods from one location to another. So really, knowledge is power, whether that be a commercial company trying to maximize profits, or whether that be a research organization that is really looking for, for answers to some of the biggest questions that are out there, like where did we come from and where are we going? Searching for livable planets out there. All of this is data that is is converted into knowledge, and that knowledge is then applied and value is derived from it. So if data is at the center, how can we actually leverage all of that data to convert it into, sorry, it's jumped a slide on me, to convert that into knowledge? We need to be able to compute on it. And to be able to compute on it, we really need to bring the applications closer to the data. Now, not all applications require the same I/O. Some applications are going to require a lot more IOPS. Some are going to require a lot more throughput. Some of them are large file I/O, some are small file I/O, some require object stores and S3 interfaces. There's a variety of different storage technologies out there, and they all provide different benefits for different types of applications. So how do we bring that all together? At the moment, people tend to create these islands of storage. They have a parallel file system, they may have some shared flash assets, they may have some cheap storage, bulk storage with hard disk drives and object stores and tape-based systems. They may have some localized storage that is inside the computational nodes for IO-intensive jobs. They may have some storage at the edge within systems, like in the car example, actually having some localized storage to be able to buffer those things. But the real answer is bring the applications to where the storage is. Create a reservoir with a variety of different storage technologies that provide benefits to a variety of different problems that need to be solved, or different types of applications or computational systems that have different requirements. So with all of this, it's all actually converging into one great big piece. We've got all of these edge IoT type systems gathering data. We've got research going into artificial intelligence, lots of machine learning that's going on, as well as traditional HPC type environments where, you know, we're actually moving to a world where all of these types of processing are really coming together and converging into the one place. And high performance computing centers are really well placed to take advantage of this convergence and provide a central hub, so to speak, for these data reservoirs where there is a large computational asset available for use on those data sets. So how do we store and protect an exabyte of data? An exabyte of data, you know, is a million terabytes. So it's a significant amount of capacity. We're quite familiar with a petabyte today, which is 1,000 terabytes. But once we start thinking about an exabyte, you know, how do you quantify that? Well, you know, an 8K movie is about 2 hours and it's about 15 terabytes. So that's like 72,000 movies that we're going to store. So the IMDb statistics say that there's a total movies out there, there's 908,000 movies. So if they were all in 8K, we would have a number of exabytes of capacity just in movies alone. So how do you store and protect that? Because, you know, at that type of scale, it gets very, very expensive. So if we think about, you know, the technologies that we have available to us today, we definitely have flash and we have NVMe, and the power of NVMe devices, you know, is upwards of 25 watts per device. Now, that's a significant amount of energy, but NVMe also has a significant amount of cost. So we don't even think about it because of those cost implications. Hard disk drives, we've got 20 terabyte hard disk drives out today. It's approximately 10 this year. It's approximately 10 watts per drive. So 20 terabyte drives, we'd need approximately 50,000 of those drives, which is going to be 0.5 megawatt of energy just to run those drives all the time, to have them spinning if they were part of a parallel file system or even an object storage environment. Unless those drives can be powered down and powered off, they're going to continue to draw that energy. When we think about tape, tape is slow, it's inherently slow, its random access really isn't that good. It's really good for large sequential streaming IO. It's really good for long-term storage and archiving. So if we think about LTO-10, tape-based devices, and the number of those tapes that would be required, the footprint is quite large, but our power and energy footprint can be as low as around 12 kilowatts or less. It depends on the number of drives that we have in the system and the performance that we want to achieve. But 12 kilowatts versus 500 kilowatts is a significant difference when we're looking at storing exabytes of data. So data management itself really is about how do we manage the data across these different tiers of storage. We've obviously at the top of this triangle, we've got the NVMe and flash devices, which are really good for high IOPS and really good for throughput as well, but they're actually a really high cost. Down the bottom, we've got tape-based technology, which is really good for large volumes of data, longevity and protection of data. But and it's low cost, but it is also inherently slow. So we really need to maintain a mix of these technologies. It doesn't mean we're going to have all 5 layers within this triangle, but we are going to implement probably 3 of these layers. And we can't think that one size is going to fit all of our requirements. But we do need a way to be able to manage the data across all of these tiers, to use those expensive tiers of storage effectively and efficiently where they are required and where it makes most sense and adds most value. But we also need to be able to free up those expensive resources when we need to. HPE's data management framework, also known as DMF, it virtualizes all of these tiers and enables us to spread out over all of those different tiers the data and have the data in the right place at the right time in the right tier of storage for a specific application requirement, as well as providing us a data protection capability within the dormant tier of storage. So Dr. Robert Bell from the CSIRO said in 2009 that data always lives longer than the hardware that it's stored on, and that forward migration to new technologies should never adversely impact the users. Now, this has never been more true than today, when we are rapidly growing in our data requirements and we're having to change those technologies quite quickly. We're replacing disk-based systems every 3 to 4 years, and we're replacing flash systems, every 3 to 5 years. We're upgrading or augmenting these systems every, approximately 2 to 3 years. So there is a significant amount of churn and change that is happening within these data-rich environments. So how do we ensure that the data is always accessible and always available? The most common thing to do is to look at triplicate replicas. The problem with that type of approach is that it is extremely costly. If we're creating triplicate on our highest tier of storage, we're having 3 copies in NVMe, which is super expensive. Even if we had 3 copies on a disk-based system, that is also super expensive. But if we had 1 copy in our performance tier and 2 copies in our dormant or a slow protected tier, we can actually minimize the amount of cost impact protecting that data actually has on our organization. So we've got all these different storage technologies, and we've got these workflows that require the different storage technologies for different parts of that workflow. We may have the parallel file system where data will reside for most of the time. We may want to promote it into a flash-based file system for a specific part of a workflow, which may only require access to a subset of the data that's contained within the main parallel file system. We may leverage cheaper secondary storage tiers with bulk disk with MAID, a massive array of idle drives, where the hard disk drives are able to power down and save on energy. We may look at object storage technologies, which are geographically dispersed with multi-site replication across multiple locations that enables us to share data as well as minimize the impact of any type of disruption to that surface. We've also got tape-based technologies that provide a secure and reliable mechanism, as well as encrypted mechanism within the hardware itself for on-site and off-site storage and the long-term storage of that. Tape has been a proven technology for the past almost 80 years now, more than 80 years. So it's been around for a very long time. We've moved through a variety of different types of tape. We're now working with barium ferrite, which is a pre-oxidized material. So it actually has a better shelf life. It has more stability and a broader range of temperatures that it can actually withstand. So tape is still strong, and it's still used by the largest companies in the world with the largest data repositories. So data management framework is a technology from HPE that can tie all of these different storage technologies together. It can be tied into a job scheduler to enable us to move the data across those different tiers of storage, ensuring that data is always protected, always secure, and always available. And it's not new. Big data is one of these things that has been around for a very long time. At the Supercomputing Conference in the US in 1996, SGI and Cray, as a combined company, coined the phrase big data way back then. So it's not something new to us. It's something we've been working with for a very long time. We weren't working with exabytes back then, but we've scaled our understanding and we've scaled our technologies to actually meet the challenge of big data in the exascale age. So the HPE ecosystem is built on the principles of the high performance tier, which is provided by parallel file systems, which HPE has an embedded IBM Spectrum scale solution, as well as an embedded Lustre solution with Cray Cluster Store. But we also, DMF can also work with NFS and NAS type systems to enable us to capture the data out of these different file systems, either natively in real time or as a scan and act approach, which enables us to actually move data between these different file systems that may be configured with different types of hardware technologies, providing different types of I/O, whether that be IOPS driven or throughput driven, or a combination of the two. Within these two file system technologies that HPE offers, we can use hybrid systems. We can actually have flash devices and disk devices within the same single namespace. DMF acts in unison with these file systems, acting on those file system changes as they occur to protect data in lower tiers of storage, including 0-watt storage, which is our patented technology for powering off and spinning down hard drives to save energy. And then we spin them up as we need them. Effectively, it's like a better tape in a way. It's a faster to spin up and get accessed. We're not waiting for the tape cartridge to get loaded into a drive. Every hard drive itself is like a tape loaded in a drive. We get the benefits of traditional hard drives with random file accesses, with the heads being able to move across the platters within those hard drives, giving us fast access to data, which enables us to do fast recalls. So we can leverage DMF to actually use a capability called dynamic namespaces, where we can spin up a temporary all flash-based file system that is geared for high performance throughput and millions of IOPS, and deliver that data, a specific data set, to that file system that has been created on demand as part of a scheduled job and allocated to a number of client nodes for the life of that job or a series of jobs. DMF can then determine any changes and push those changes back into the managed file systems, whether that be IBM Spectrum scale based with HPE's parallel file system storage, or Lustre based with the Cray Cluster Store E1000. But we can also push data into NFS file systems. We call that staging, and we can pull data out of NFS file systems, which we call destaging. This is effectively copying data into and moving data out of, moving data into and moving data out of those NFS-based file systems. So this ecosystem that HPE has created enables us to take our high-performance computing platforms that we have with GPU-enabled platforms and CPU-enabled platforms that are both air-cooled, direct water liquid cooling, or containment-based solutions, and we can work with a variety of different storage technologies that may be required. We're anything from scale-out hard drive solutions, whether that be NAS-based, Lustre-based, or GPFS-based. We're looking at DAOS at the moment and working with Intel on DAOS with a number of customers that are early adopters today. And we're looking at how we can integrate that into our ecosystem with DMF being that central data management hub where it's possible for DMF to monitor and manage these different file systems, understanding what data is stored where and what data needs to be placed in another location to meet the requirements of a job that has been scheduled. We can use DMF to create copies of data like replicas. We can push data into long-term archives, whether they be cloud-based or tape-based, on-site or off-site. And we also leverage DMF with an extensive metadata indexing engine so that we can search for data that may have been collected from a variety of different platforms, and it's all stored in one central location. It can be automated and it can be easily maintained. Any errors are automatically detected and repaired. DMF constantly maintains 2 copies of all data on different media within its data stores. DMF's ability to be able to capture data as it's created, checksum it, store those checksums with the data on the media, store those checksums within the DMF database, guarantees that the data that we read from the managed file systems is the data that we store in the lower cost tiers, whether that be cloud, 0-watt storage, or nearline tape. When we read it back, we do the same process, but in reverse. We read the checksum back from the tape. We check it on the data that has come back. We check it against the checksum that we've stored in the database. We then push it out and write it back into the file system, knowing that bit for bit, we've recreated exactly what data was stored within that file system when it was created. And that's the last slide I have. I might have finished slightly early. If there are any questions, I'm more than happy to respond to them.
Just want to say. Hi everyone. So this brings us to the end of day 2 of the industry track and of the Supercomputing Asia 22 conference. I hope that you all had a very interesting afternoon, that you've learned a bunch of new things. And before we bid farewell for today, I invite you all to scan this QR code and give us feedback, both those that are here in person or those that attend virtually. And I wish you a very nice evening and see you tomorrow. Thank you.